Problems of conduction. Uh, Today class, my name is Rudresha S. Today class I will teach from governing law of conduction. Q proportionality A. See, look at here, governing law of conduction. Governing law of conduction Q is depending on heat transfer rate is depending on uh, heat transfer. Heat transfer rate depending on area. Heat transfer depending on area. Heat transfer rate here heat transfer rate depending on area. Q is proportionality A. Q equals minus KA into dt by dx. Q is equal to heat transfer rate in watts. A is equal to area of the surface normal to the heat flow direction in meter square. And dt by dx is equal to temperature gradient. dt by dx is equal to temperature gradient. Temperature gradient dt by dx is equal to temperature gradient. See, this is the governing law of conduction. Governing law of conduction heat transfer. The second equation is Newton's law of cooling or governing law of convection heat transfer. Governing law of convection heat transfer. Q is equal to HAS TS minus T infinity. Q equals heat transfer rate in watts. A is equal to surface area exposed to the heat transfer in meter square. Ts is equal to surface temperature. T infinity is equal to room temperature degree Celsius. H is equal to heat transfer coefficient. This is the Newton's law of cooling. This Newton's law of cooling will be depending on convection. There are two types of convection is there. One will be forced convection, another one will be natural convection. There are two types of convection is there. One will be there are there are two types of there are two types of heat transfer. There are two types of heat transfer. Heat transfer. There are two types of heat transfer. One will be first one will be natural convection. First one will be natural convection. First one will be natural convection. Second one will be forced convection. Forced convection. See here, See, radiation of heat transfer, Q is proportionality A into T to the power 4. C A into the alpha is equal to C. Q is depending on epsilon into sigma AS into T to the power 4. Q to the power 4 is equal to surface temperature which heat is emitted in Kelvin. AS is equal to surface area in meter square and sigma is equal to Stephen Boltzmann constant 5.67 into 10 to the power of minus 8 watt per year. Just write it here. The Stephen Boltzmann constant 5.67 into 10 to the power of minus, this is 10 to the power of minus 8. 10 to the power of 10 to the power of minus 8. 10 to the power of minus 8 watt per meter square into k to the power of minus 4. This is the Stephen Boltzmann constant. Next, this is the Stephen Boltzmann constant. There are three equations very, very important in transfer the heat. Next, I will move from the problems on heat conduction. Problems on heat conduction. Look at here, the inner surface of the furnace wall is at 200 degrees Celsius and outer surface at 50 degrees Celsius. Calculate the heat loss per meter square area of the wall. If thermal conductivity of the brick is 0.5 watt per meter degree Celsius, the wall thickness is 200 mm. See here, all the values is given data. The inner surface of the furnace wall T1 200 degrees Celsius and outer surface at 50 degrees Celsius. Outer surface at 50 degrees Celsius. K is equal to 0.5 watt per meter degree Celsius. See one more, length of the plate. Length of the plate equals length of the plate. Length of the plate. Length of the plate equals 200 mm. Length of the plate 200 mm is equal to 0.2 meter. 0.2 meter. 0.2 meter. See here, I just draw the furnace wall. I just draw the furnace wall. I just draw the one furnace. This furnace, see here, text T1 is equal to T1 is equal to 200 degrees Celsius. T1 is equal to 200 degrees Celsius. T2 is equal to T2 is equal to 50 degrees Celsius. T2 is equal to 50 degrees Celsius. L is equals L equals 0.2 mm. 0.2 mm. 0.2 mm. C. Calculate the heat loss per meter square area of the wall. you have calculate how much heat loss per. See, what is meaning by study one-dimensional heat transfer? Heat will be transferred in one end to other end. That is calling about one-dimensional heat transfer. See, L is equal to dx is equal to 0.2. See, 200 mm. Next, look at here. T1 is equal to C 0.2 mm is length of the furnace. C heat loss is equal to minus Ka into dt by dx. Heat loss per meter square 0.5 into 150 in minus 200 0.2. The value is equal to 375 watt per meter square. Q is equal to 375 watt per meter square. Heat loss per meter. Heat loss per heat loss per meter square area of the wall, heat loss per heat loss per heat loss per meter square heat loss per meter square 375 watt per meter square. Next, radiation of heat transfer. What is meaning by? See here the second problems. One face of a copper plate 3 centimeter thick is maintained at 400 degrees Celsius. Other place is maintained at 100 degrees Celsius. How much heat transferred through the plate? Thermal conductivity of the copper. How much amount of heat transfer through the plate? Q equals Q equals Q equals say Q is equal question mark. You find out the values. Find out the values. Q is equal find out the values. See L is equal to dx, the length of the plate 3 centimeter. Temperature difference dt is equal T2 minus T1. See T2 is the just I will draw here the wall means furnace. Just I will draw the furnace here. Just I will draw the furnace here. See here, you have a 400 inner temperature. You have a T1 is equal to this is the T1 400 degrees Celsius and T2 have 100 degrees Celsius. See here, K is equal to 370 watt per meter degree Celsius and T2 is equal to 100 degrees Celsius. And Fourier law of heat conduction, Q is equal to minus Ka dt by dx, Q is equal to minus Ka dt by dx, heat flux is equal to small q by A. See here the equation, this is the heat flux, K is equal to 370 and you have a T2 temperature is 100 degrees Celsius, T1 is equal to 400 degrees Celsius and that you have in the length 0.33 centimeters that will be converted to meter. The Q heat flux is equal to 3.7 into 10 to the power 6 watt per meter square, 3.7 megawatt per meter square. This is the value for heat flux. Heat flux, if we find out, small q equals heat flux is equal to heat flux is equal to heat flux is small q is equals small q equals 3.7 megawatt per meter square. This is the um, see here the point number 3. A furnace wall 200 mm thick uh, is made up of material having thermal conductivity 1.45 watt per meter Kelvin. The inner and outer surface are exposed to the average temperature of 350 and 40 degrees Celsius respectively. If the gas and air film coefficient 58 and 11.63 watt per meter square Kelvin respectively, find the rate of heat transfer through a wall of 2.5 square meters. Also find the temperature on the two sides of the wall. C x is equal to 200 mm, 0.2 meter. K is equal to 1.45 watt per meter Kelvin. A is equal to 2.5 meter square and TA is equal to 350 degrees Celsius, 350 plus 273, 623 Kelvin, TB is equal to 40 degrees Celsius, 313 Kelvin. See here HA and HP. HA is heat transfer coefficient 58 watt per meter square Kelvin. HP is equal to 11.63 watt per meter square Kelvin. C Q is equal to A into TA minus TB 1 by HA plus X by K plus 1 by HB. Look at here. See 3214 joules per second. This is the rate of heat transfer. Rate of heat transfer is equal to rate of heat transfer equals rate of heat transfer is equal to 3214 joule per second. Next T1 is equal to temperature on the inner side of the wall. T2 is equal to temperature on the outer side of the wall. CQ is equal to HA into ATA minus T1. T1 is equal to 600 0.84 Kelvin. And C similarity Q equals HB into A. This is Newton's law of cooling. See, you have in transfer of heat, there are two sides. One will be inner side, another one will be outer side. Another one will be outer side. See here. See, this is the inner side. This is the inner side. Inner side. This is the outer side. outer side. See here, this is the TA and this is the TB. See, inner side TA and outer side TB. You have find out the E transfer coefficient. See here, this is the inner side will be convection mode of heat transfer. Inner side will be mode of convection. The convection mode of heat transfer, and this is also convection, convection, and this is the conduction. Conduction. See, look it here. First, you have a convection plus conduction and convection. See, the inner surface of the wall and outer surface of the wall, it will be transferred mode of conduction, and the center will be this is inner and outer side will be convection, and center will be conduction. See, a cylinder having its diameter 30 centimeter and length is 60 centimeter as hemispherical ends, giving on overall length 90 centimeter. The cylinder, which is maintained at a steady temperature of 60 degrees Celsius, is covered to a depth of 5 centimeter, lagging which as coefficient of conductivity 0.14 watt per meter Kelvin. Calculate the rate of heat loss if outer surface of lagging is at 30 degrees Celsius. Q is equal to 5L into K T1 minus T2 denominator by ln R2 by R1. C 25 0.6 L and 0.14. This is the thermal conductivity. This is the length L 0.6. 60 minus 30 and ln 20 by 50. This is the Q is equal to 55 watt. And next Q is equal Q equals 55 watts. And next, rate of heat loss from the spherical portion, rate of heat loss from the spherical portion, 4 K R1 into R2, T1 minus T2, denominator by R2 minus R1. Q is equal to 31.667 watt. Yes, total heat loss 55 plus 31.66, 86.667 watt. 86.667 watt. See, convection, air at 20 degrees Celsius, overall hot plate 50 into 75, 0.5 into 0.75. CW is equal to 250 degrees Celsius and H is equal to 25 watt per meter square degree Celsius. From Newton's law of cooling, HA into TW minus T infinity. H is equal to 25 into 0.5 into 0.75. 250 minus 20. Q equals 2156525 watt. See 2.156 kilowatt. See here to find the heat transfer rate Q equals 2.156 kilowatt. These are the problems on conduction and convection. See here, totally there are plane wall and composite wall. First will be solve the problems on plane wall. Plane wall. Second one is composite wall. Composite wall. Composite wall. Plane wall. Composite wall. And plane cylinder. PLA. Plane cylinder. Composite cylinder. Composite cylinder. Plane cylinder. Composite cylinder. Plane wall, composite wall, plane cylinder, composite cylinder. Spherical cylinder and composite composite cylinder. So